Okay, hi there. Welcome to another episode of Science and Technology Q&A for kids and others. And we seem to have all kinds of interesting questions saved up from before. Let's see, the first question here from Crunchy. Oh, this is not an easy question. The question is, why does the universe exist? And that is something I've been thinking about quite a bit recently. I'm not sure how far I'm going to be able to go here on describing that. I wrote a piece about that question fairly recently, but let's try and understand the nature of the question. Why does the universe exist? Another way to put it is, why is there something rather than nothing? Another thing we can say, so the first thing we can say is, can we make a model for the universe? Can we make an abstract formal system that describes how the universe works? Can we, for example, make a program which, if you ran the program, it would simulate everything that happens in the universe? Well, let's say we can be successful at that. We've got a program which, when we run it, will reproduce what the universe does. So it's like we're running a simulation game, and it is the universe, so to speak. It reproduces all of the physics of the universe. It reproduces the sun and the planets and black holes and everything about the universe. The program is reproducing that. So in other words, we could tell the program, with the program, we could make an image. We can make a picture of, what does the night sky look like? And there will be a picture on the computer with pixels representing stars and things like this. But the question is, that's not the universe. That's a simulation, a model of the universe. That's us representing the universe on a computer. The question is, why does the actual universe exist? Why is that actualized? Let's say we have that model, and that model would reproduce the universe. The question is, why is the universe with actual stuff, like, actual physical things that we can pick up and do things with and so on? Why is that actually here, as opposed to just there being a simulation model of what's here? Okay, that's the challenge. So first thing is to have a model that does reproduce the universe, and we're getting quite close to that with our physics project. We think what at least the framework for that model looks like. Okay, but the question is, given the model, why is it actualized? Why is it turned into the actual universe, starting with a Big Bang and doing everything the universe did? Okay, this is where things get a little complicated. So let's see how to do this. The first thing to realize is that our experience of the universe is, well, we are a part of the universe. We are experiencing the universe, but we are also part of the universe, so to speak. And so we're in this simulation that we're talking about, we are pieces of that. We're pieces of what's going on there. And so the question is, we might say, for example, I might look at the simulation. The simulation might have a model of, a person I know in it. And I might be able to look at the simulation and say, the person I know is behaving just like I know they would behave. And of course, I'm not inside that person, so I can't tell from the inside whether that person feels that they're really there. All I can tell is from the outside, I can see the simulation, and that person looks like they're doing what the person would actually do that I know in real life, so to speak. Okay, but for me, I'm like, I actually exist, and I'm not just a simulation of me, so to speak. Okay, how does this all unravel? Well, the key observation, let's see how best to get to this. Okay, so let's go from a different direction. Let's say you have a model of the universe, and you might say, why is it that model of the universe and not another model of the universe? Why does the universe work according to this particular model? You might say, it's like the question of why is there something rather than nothing? Why is there this particular thing rather than something else. You might say there's got to be some sort of godlike figure who must have picked, these are the rules for the universe. This is what I want to run. This is what will turn into the universe. I think there's a nice kind of version of that from a philosopher named Spinoza from the 1600s, I guess, where he described the universe as the thoughts of God actualized. So it's kind of like there's sort of a logical thinking process that's going on, and the universe, in his picture of what was happening, is that sort of logic of thoughts, and the logic is what leads to laws of physics and so on, and it's those being actualized that make our universe. So, okay, so the next question is, why is it this universe and not another universe? Okay, so in our models of physics, one of the things that happens is that there can be, given the structure of the universe, given a state of the universe, there can be many different possible states which the universe goes into at the next moment in time. And in fact, there's this whole branching and merging structure, this whole multi-way graph of possible histories of the universe that can develop. And one of the things that we realized is that quantum mechanics, sort of a key piece of physics, is the result of this kind of branching and merging of histories of the universe. So in a sense, there isn't a unique history for the universe. There's not a unique set of things that happen in the universe. There are many possibilities, and they're all happening. And so one of the questions then is, well, why do we perceive a single set of things to be happening in the universe? And the answer, which is a little bit hard to understand, is, well, we are part of the universe. So in a sense, if the universe is going in these many branches of history, so are our brains. So it's kind of the story of how does a branching brain perceive a branching universe. And it's merely the fact that we have the idea that the universe does a definite thing that causes us to sort of knit together those different branches of how our brain is behaving to say, well, actually, the universe is doing this definite thing. Okay, so it turns out you can go even more extreme than that. Not only does the universe follow a particular rule, but apply it in many different ways, so also the universe can actually follow all possible rules. And in some sense, I think the universe is following all possible rules. Now, you might say, how do you then conclude anything? It's like, if the universe can follow all possible rules, it's like not everything, every possible thing can happen. So how can you ever say anything in science or otherwise? Well, that's not the way it works, because the point is that as soon as you say all possible rules can be followed, and it can be the case that, and you're starting from many different possible states, you get to many different possible states, you get this complicated network, because you can say you start from a state, there are two rules that apply, they lead to two different states, then there are several rules that apply there. And one of the things that can happen is the states that you get to from those two different states can merge and be the same state. So what you end up with is this complicated, entangled graph of states that you get to by applying different possible rules. And even when you're applying all possible rules, the thing you get is not just a nothing. It's a very complicated structure with a very complicated thing with very definite structure. And in a sense, that is the universe of all possible universes. That's the entangled version of the histories of all possible universes. They're all tangled together. And so then in a sense, then it's not a question of, well, which universe gets picked? It's all universes are getting picked. They all have these complicated, entangled histories. And so then the question is, well, if we are perceiving the universe, if we're observing what's going on, we are also part of this complicated, entangled universe of all possible universes, sort of history of all possible universes thing. And what we realize in the end is that it is, as entities embedded in this, we perceive what's going on. We can only perceive some small slice of all these possible things that are happening, because we are in a sense, observers who are able to do only a certain amount of computation and so on. We are only capable of perceiving a small slice of this sort of history of all possible histories object. Another way to look at it is in physical space, we live at a particular place in the universe. And it's a huge amount of effort that we haven't been able to do to like travel to a different galaxy or whatever else, to move around in physical space. We also live at a particular point in what we call rulal space, the space of all possible ways of perceiving the universe, so to speak. We perceive the universe in very particular ways. There are an infinite set of possible ways you could perceive the universe, but we perceive it only in a particular way. So it's in a sense, we're at a particular place in physical space. We're also at a particular place in rulal space. And the thing to realize is the universe that's out there in rulal space is this universe of all possible histories. And no choice had to be made in producing that. The choice is, where in rulal space do we happen to live? Just like where in physical space do we happen to live? And that determines the details of our experience and perception of the universe. So now the question is, why, the original question said, why does the universe exist? Well, the answer is that this structure that we get from following sort of all possible rules is the inevitable structure that you get by following formal rules for things. So like you might define 1 plus, and then you say 1 plus 1 equals, define equals, define 2. It's inevitable, given the definitions of 1 and plus and equals and 2, that 1 plus 1 is equal to 2. That's not something where you have to actualize anything. That is an inevitable formal fact. And so what ends up happening is that you realize that the set of all possible formal facts is, and their consequences, their sort of computational consequences, is the thing that creates this object that is this history of all possible universes. And the fact that there's no real issue of why that exists, because it is a formal fact that is a thing that can be constructed formally, just like you can formally construct 1 plus 1 equals 2. You don't have to say, I have these one stone and another stone, and you put them together and it's 2 stones. So in a sense, the question of sort of why the universe exists is this statement that in fact, the universe exists because it is constructed from these purely formal objects, and it is all possible formal objects. And so there's no, oh, we're picking this particular one to exist. It's like all possible formal objects, and you can kind of construct any of them. And then our perception of the universe is based on sort of living at this, experiencing it from this one particular point in this rulal space. This is a complicated subject, and I hope that gives at least some flavor of how one can answer that type of question. That one of the interesting consequences is that insofar as the universe exists according to this argument, so also mathematics exists. And one might think of mathematics as something where you just decide, I'm going to set up certain rules for mathematics. I'm going to say x plus y equals y plus x. That's a rule, that's an axiom for mathematics. And I'm going to build mathematics up from axioms. And that's been for the last 130 years or so, that's been kind of the traditional view of kind of what mathematics is. It's something where you pick a set of axioms, a set of principles for how geometry works or arithmetic or something like that, and then you build up all the consequences of that from those principles. What this realization about the universe and its existence implies is that there's actually an object that is not picking particular sets of axioms, but it is an object that represents the consequences of all possible axioms. And that in a sense, mathematics, as we practice it, is really just looking at little tiny corners and slices of this object that represents all conceivable mathematics. It's a somewhat different view of mathematics. And there are things that one can imagine are global features of this sort of universe of all possible mathematics is, just as there are global features of the physical universe of all possible universes. And those global features turn out to be laws of physics that we know, like laws of gravity, laws about quantum mechanics, and so on. And so we don't yet know what those corresponding sort of global laws of the mathematics of all possible mathematics will be like. But that's a thing. Well, I'm actively studying that right now. Don't yet have good answers to it. But okay, that was a pretty complicated set of ideas. So, well, here's a something a bit simpler to answer. Baker asks, when was the last time I wasn't the smartest person in the room? You know, I don't know. I'm not a person who measures, who believes in kind of a linear scale of smartness, so to speak. I think the thing that is always surprising to me about all the different things I learn about and all the different kinds of things I do is that there are people who are just way better than I am at doing one thing and way worse than I am at doing something else. And so, for example, when it comes to mathematics, there are many different kinds of ways to think about mathematics. And so there are places where, yeah, you know, I'll understand something and like many people I know will be like, I don't understand that, and I managed to understand it. And there'll also be things where other people can just say, oh yeah, it's obvious, that's how it works. And I'll be like, what on earth are you talking about? I do not understand that at all. So it's something where I think we, based on sort of some intrinsic skills that people have and based on what people have learnt, they're just very different things that people are capable of figuring out and not. I mean, I think sometimes the challenge for people, just as a sort of a people development kind of thing, is to figure out what kinds of things you actually are particularly uncommonly good at figuring out. Because for many people, there will be things that they are uncommonly good at figuring out. The question is, can they figure out what those things are? Like, you know, some people might be really good. Like one of my kids she's really good at kind of spatial visualization of kind of 3D objects and visualizing what they're like and how they work. I'm useless at that. She happens to be a math graduate student working on things related to geometry. So that's a good kind of match for, well, she's really good at that particular thing. And actually she's doing something which makes use of that particular thing. It's not, there are skills that might be ones which would have been really good to have 300 years ago in the development of civilization then, and maybe it's not so obvious to apply them, how to apply them today. Like you might be, well, even in my lifetime, you might be really good at like reading maps and understanding how sort of things spatially relate to each other. And of course, reading maps is, I don't know whether it's completely a lost art in the world of GPS, but it's definitely not as prominently important as it perhaps once was. Of course, there's still plenty of things about visualizing sort of layouts of things in space that are still plenty important in lots of areas. So I think my experience tends to be, you know, if you kind of choose to hang out only with people who know about the same kinds of things you know about, and you know, one of the things that happens to me is that, you know, I've been studying lots of kinds of things in science and technology for my whole life, pretty much. And I have a pretty good memory. So I've kind of, you know, I've accumulated a lot of experience. And so quite often it will be the case, if I'm kind of dealing with things where I really know quite a bit about them, that yes, I'll be in a situation where I just remember, oh, I saw something like that 30 years ago. And so I just know the answer immediately, cold, because I've seen that problem before. I saw that 30 years ago, so I know the answer. It's if one's confronted with something new, it's a question of, can you figure out sort of the new answer? And that's something, well, I like that a lot, kind of figuring out from first principles what's the answer to something. And sometimes I find it very disorienting when I run into people who are good at, as I sort of, they're good at sort of operating at a level where I don't understand the pieces that are being put together, but they can come up with conclusions, even though the pieces don't seem to be well anchored into anything. And they can even come up with correct conclusions. And for me, I tend to have to build things up where I sort of understand the foundations, then I go to the next level and the next level and so on. And it's been interesting in our physics project. there are different people who've been working on sort of the front lines of our physics project and who think about things in different ways. And some of them are much more in the kind of the sort of the tortoise-like approach of slowly going from the foundations and building up one layer on top of another, which is kind of the most common thing for me. And there are others where they're kind of going from these very abstract ideas and being able to connect them together and come up with conclusions. So, you know, in my own life, I suppose one of the things that I learned very early, I happened to go to a kindergarten in Oxford, England, where there are lots of smart kids. And so I think from the age of 3, I never particularly thought of myself as the smartest person in the room, because I probably wasn't in many measures of these different kinds of things. Anyway, a fun question, a bit easier than the why does the universe exist question. All right, so many more questions here. Oh boy. Okay, there's a question here from Simple. If all knowledge about physics was lost, which theory will be the most difficult to rediscover and why? Well, a good question. I mean, the things we've been working on with sort of our approach to fundamental physics now that I started about 30 years ago, a good test case for that is, would that theory have been found if, you know, we hadn't worked on finding it? I think the answer is, I think it would have taken at least another 50 years, maybe 100 years. I think it is something where what's kind of happened is that every field develops in a certain direction, and it has certain sort of ideas that seem like they're self-evident and intrinsic to the field. Like in physics, oh, you build these mathematical models and you construct things in this way, and so on and so on and so on. And to get to the place that leads to kind of our approach to fundamental physics, you kind of have to go in a different direction. And you kind of have to think about things in terms of computation. There are, you know, I haven't really cataloged it, but I think there are at least a dozen kind of things that one used to believe were true that you have to realize aren't right to get to this theory of physics that we have. So in other words, given where things were, it's a complicated jump to get to where things should be. Now, having said that, once you understand this fundamental theory of physics that we've been developing, it turns out lots of things people have been doing over the last 30, 40 years are building in very much in this direction, but it would have taken a long time, I think, to get to the kind of clean structure that we found in this theory for fundamental physics that we've developed. There are lots of things where it's like, well, once you see that basic theory, you can start seeing, oh, this plugs in here. This is why this complicated mathematical thing works this particular way. But it would have been really hard to go from that complicated mathematical thing to this essentially much more simple sounding foundation for physics. So that's one where, you know, I'm seeing that in real time. It's like, if we hadn't done this, how long would it have taken for people to get to the same place? I think that if we look at a case that I think is quite analogous, which is the history of computation, the history of ideas about the theory of computation. The sort of the key moment in that was probably the invention of Turing machines, a little bit the invention of lambda calculus, but I think much more the invention of Turing machines. Turing machines are these idealized models of computers invented in 1936 by Alan Turing that are very concrete. They talk about, you know, you write down this line of boxes, and each box has a value in it, and you have this head that goes up and down the line of boxes, erasing the values, adding values, and so on. It's a very concrete description. Well, people had things a little bit that in the end turn out to be equivalent to that. They'd had those, well, certainly for 16 years, at the time when Turing machines were invented, but a whole collection of these: lambda calculus, general recursive functions, combinators, post-production systems, just a whole bunch of different kinds of things. But none of them, they were all kind of complicated and abstract and had a lot of structure in them, which kind of didn't make it evident what was really foundationally going on. And so it took the invention of kind of this very concrete idea of Turing machines. Then you could say, well, actually, it's the same as lambda calculus, and it's the same as this, and it's the same as that. And then you can build this bigger theory on top of that. But it took those pieces to get to that point. And so I think that's it's one of these things where there are these places where there's clarity that can be gotten, but that clarity is not easy to get once you've built a deep and complicated theory. Now, the history of physics could have been different. For example, I'm fond of thinking about if computers had existed in a long time ago, how would the history of science have been different? Like the Antikythera device, which comes from around, well, between 100 BC and 100 AD. It's this sort of clockwork computer used for computing astronomical things. And it's a fairly elaborate mechanism that existed in antiquity. We have only one example of such a thing. There's only one that was found from a shipwreck that was discovered around 1900. But I don't know how common those things were in the ancient world. And nobody kind of knew about the tradition of making those things from basically 0 AD up until about 1600 AD when the ideas were reinvented. But let's say there had been many more computer-like things, clockwork computers that had existed in ancient times. And let's say they'd been really common everywhere. Would people have thought about the development of science in a different way? And perhaps they probably wouldn't have had electronic computers, but you don't need electronic computers to do computation. I mean, for example, in the 1840s, Charles Babbage and Ada Lovelace and so on had conceptualized this idea that you could make a purely mechanical, cogs and rods and levers and so on, computer that would be able to execute programs. Actually, it's fun to see the question of whether these purely mechanical computers, where instead of using electronics and electricity to make a computer, you're just using levers and gears and so on, where's that useful today? And there's kind of a fun use that I ran across a few years ago now, which is if you want to send a spacecraft to Venus, the surface of Venus is, I don't know what, 300 degrees centigrade or something, very hot. And most things just melt at that temperature. And certainly standard electronics can't operate at that temperature. But so if you need a computer on the surface of Venus, how are you going to get it? Well, you can do something really exotic. You can run the clock back 150 years, and you can say, let's use those analytical engine techniques that Charles Babbage and Ada Lovelace worked on, and make a mechanical computer for our spacecraft for Venus. But that's just sort of a fun thing. But how would the history of science have been different if computers had been common? I think, for example, our theory of physics would have been invented long before the theories of physics that are based on elaborate kind of mathematical ideas. But we can't get to rerun history and see that. Let's see. There's a question from Davar about Wolfram Alpha, and saying, yes, we don't use, the idea of knowledge graphs is this kind of weird idea that kind of came out of the early history of AI, that knowledge is somehow best represented by a graph of what's related to what. And yes, some knowledge is representable that way, but that's not a great way to represent all knowledge. It's kind of a silly way to represent all knowledge. I think that the history of representing knowledge has an interesting history. I mean, at some level, our natural language is a representation of knowledge. When we start writing down our natural language, that's a way of representing knowledge. Then there's sort of more formalized ways of representing knowledge. One that people thought about for quite a while is logic, you can say, let's represent everything by making logic statements, particularly statements in so-called predicate logic. So logic, there are two fundamental kinds of logic. There's propositional logic, as described by Aristotle in Antiquity and so on, which is, he didn't describe it in a slightly different way, but in modern terms, we would describe it as things like, it is sunny today and it is hot outside today. And we could say it is sunny today implies it is hot outside today, and then we could say, or it is raining today. So we could say it is sunny today or it is raining today, but both of those can't be true. And we can kind of make logical inferences based on ands and ors of statements and so on. And that's so-called propositional logic. And that's a kind of logic that is ultimately what computers use to set up how their CPUs operate, is by doing sort of billions of logic operations like that with ands and ors and such like. That's a sort of a simple way to represent some kinds of things in the world. Then there's the idea of predicate logic, where instead of just saying it is raining today or it is sunny today, you say for all, the famous one is, all men are mortal, Socrates is a man, therefore Socrates is mortal. And this is starting to use sort of the idea of these predicates that say things like, for all such and such, or there exists a such and such, so that whatever. There exists a, there exists on a line, there exists a point between any 2 points on a line or something, I don't know what. You can say there exists a whatever. So you can start to build up knowledge represented as, for all. You could say something like, for all, what's a good example of something that's real world knowledge? For all countries, you might say, there exists a capital city. That's probably not true. In fact, I know it's not true. There's somewhere there are multiple capital cities and other such things. But you could try and start encoding knowledge about the world, as in, for all countries there exists a capital city, and so on. So people tried to do that in the early history of artificial intelligence. People tried to encode knowledge using logic. It really worked very poorly as a practical matter. Then people had the idea, let's just encode things in terms of, we've got these entities like a planet, we've got these properties like, has moons or something. And we say, let's just encode things in terms of the sort of graph, or a graph that says things like a planet, the planet Mercury is part of the solar system, things like that. And, we can say things like such and such a person is part of this sports team. Or there are other things in the world that you can represent pretty well in terms of these kinds of, a thing is a part of another thing, or a thing has some property with respect to another thing. But there's an awful lot of knowledge that does not get represented that way. So for example, if you're talking about planets, you can say Mercury is a planet in the solar system. Great. That's a sort of a fact about Mercury. But there's a lot like, where is Mercury right now? What is the orbit of Mercury? How do you work out the orbit of Mercury? What is the distance between Mercury and Earth right now? That has nothing to do with a, quotes, knowledge graph of what is the relationship in terms of, does Mercury have the property of being a rocky planet? Is Mercury a part of the solar system, and so on? So these kinds of models of knowledge that are kind of static models, where they're like, this is a part of that, this has that property of that, for all this is it's of that. Those models of knowledge turn out to be quite limited. And the things we as a civilization know, particularly from the last 300 years, from a time when things like the mathematical sciences have existed, now the computational sciences exist, the kinds of knowledge that we get from that are not well represented by this kind of static idea of a knowledge graph. Yes, if you're trying to figure out, what products does a company have, and that might be representable by just there's a company, it has these products, each product has these components, et cetera, et cetera, et cetera. That's representable by a graph of connections. But in general, that's a very poor model of the knowledge that we as a civilization have accumulated. And in building Wolfram Alpha, our goal has been to try and make the knowledge that we as a civilization have accumulated, make it computable in the sense that we can readily, if you ask a question that can be answered on the basis of that knowledge, we can compute the answer. And for that, we've ended up using kind of the full computational language that we built in Wolfram language, which is kind of a full representation of the kinds of things that can exist in the world and so on. And it's quite different from this just pure graph of this is connected to that. Now, of course, we have a lot of data that is in the form of this is connected to that, but that's not the whole story. And so ultimately, the data that we get about the world has to come from somewhere. And what we've done over the course of the last 20 years is to kind of go to the primary sources and sometimes compile them ourselves of data about the world and be able to sort of connect to those primary sources of data. And it's a very difficult business because you really have to understand each kind of data in order to do a decent job of seeing how that data should be connected to other kinds of data and so on, and how you can compute things from that data. And it's sort of a very different activity. The activity of kind of sort of let the crowd curate data. We have had a bunch of volunteer curators and so on who've been very helpful to us. But in general, the let the crowd curate data tends to be a fairly poor solution for many things, because it's like then you get all these different things curated in all these different ways. And what we need is something very systematic that we can actually do computations from. And so that tends to be our model. Now, things like Wikipedia has certainly, quite a lot of what's in there is nonsense, but quite often what happens is that there'll be some primary source of data and somebody will kind of a little bit of a ripoff, take that source of data and sort of spray it in different parts of Wikipedia. And then people will say, well, actually, I know more about this particular part. I'm going to change that particular thing. Well, that means whatever consistency there was in those pieces of data that have been put in different places is no longer there. So if you go and you say, I'm going to scrape all these things from Wikipedia, you'll end up with something completely inconsistent. And but Wikipedia, what it has that's very interesting and very useful is kind of folk information. Like, what is the typical name by which this town is called by locals, so to speak. And that won't be the official name that is in the government census and so on necessarily. It'll be a thing that's sort of folk information. And that's a thing that's very well collected, but it's something that is almost, it's sort of the opposite problem from the problem of making it very systematic data. So let's see. There's a question from Wick, I think. Kids and teenagers, they say, are less and less interested in mathematics. What do you think is the reason for this? How would you change it? Well, I don't know. Some kids and teenagers are interested in mathematics, but yeah, plenty are not. And I'm afraid one of the things that's tended to happen is that there's a sort of mechanical kind of mathematics that is, do this calculation, do that calculation. That's a very convenient thing for people to use as part of the education process, because you can just say to a kid, well, here's 100 math problems of this kind, go off and do these. And you'll learn some skill in doing those. But by the way, you can also assess easily how well did that kid do on those math problems. It's a very sort of easy loop that's kind of like a production line for sort of learn these things and be able to learn sort of the mechanics of how to do them and then test what whether you were able to learn those and so on. And so the this is kind of the this has been kind of a, public education in mathematics has been going for what, 130 years or something now. And unfortunately, the exercises that are done haven't changed very much over that period of time. In fact, even if you look at the very earliest calculus books from like the 1730s, you'll find some of the same exercises there that people have in calculus books today. Of course, a big change over that period of time has been the arrival of computers. And a lot of those kinds of things that people would do mechanically with mathematics, we can now do instantly. And I've personally been responsible for building some of the technology that makes that possible. We can do them now with computers, with Wolfram Alpha, with Mathematica, with Wolfram Language, and so on. And so then the question is, okay, if you can do those things automatically, then what can you then see in mathematics? What can you then get to in mathematics? And the answer is you can get to some really interesting things. Not only can you do much richer, deeper mathematics itself, and you can do sort of experiments in mathematics, but also you can use mathematics because you can use much more realistic mathematics to reach kind of things that relate to our kind of everyday world. Now, does that mean it isn't worth learning the kind of the mechanics of how to do mathematics? It's worth learning the mechanics of how to do something precisely. Whether mathematics and integrals and calculus is the best thing to learn that about is not clear. I think it's better to learn that about writing computational language, which is another thing that requires sort of precision and kind of very systematic thinking to be able to do well. It has the nice feature that when you're writing computational language, you get immediate feedback. It's kind of like, well, it worked or it didn't, rather than I hand in my homework and the teacher says I did that algebra correctly or not correctly. It's something where I can kind of immediately see for myself, did the computer do what I intended it to do? It's also something where you get sort of the leverage of all of what we built in computational language and so on, and you get to the point where you can immediately connect with things about the everyday world. So I think there's the fact that one of the things people take away sometimes, or quite rather often, from learning math in school is, oh, I'm not very good at doing this. Oh, it's really kind of boring. It's really kind of horrifying that those are the things people take away from their experience in mathematics. Now, it's certainly the case that not everybody will be a mathematician. Not everybody will get into the kind of the fine details of the very elegant results of mathematics, the very elegant things that can be done in mathematics. But you don't get to see any of that often in sort of at the ground level doing this mechanical stuff, which realistically can be done well by computers today. So I tend to think that there are three things that you get out of kind of doing math. Think about three. One of them is just learning how to do something precisely. It could be writing computational language, writing programming languages, things like that. But some math, it's good to learn. And it's good to know how to do something systematically and precisely. One sort of exercise that I kind of have described about math and sort of mathematical thinking is somebody hands you a cube and they say, label the corners of the cube. How would you label the corners of the cube? And somebody might just say, well, label this one number 1, this one over here, number 2, number 3. Okay, but be systematic. Think about that systematically. What will be some systematic ways? There isn't a right answer to this, but how would you think about that problem of labeling the corners of the cube? If you're kind of used to doing mathematical kinds of things and thinking about things in a mathematical way, you think about very systematic ways to label the corners of that cube, rather than just, well, I do this one and then this one, and oh, I forgot about this one. Let's put that one in next. And it's useful to know how to sort of do things systematically like that, think systematically. Another thing is that it's useful to know what math can do, what kinds of things sort of are accessible to math, what kinds of things might you be able to work out using math. Even if the math is actually being worked out on a computer, what kinds of things does mathematics allow you to figure out? Like if you say, well, there are these two, let's say you see a bunch of recommendations for some product and some are very good and some are very bad. And you're saying, and you're comparing two products and it's like, which product is better? And you see this whole range of different scores for these two products. How do you compare those? Again, it's a question of thinking about mathematically. Do you know about means and medians and how do you compare distributions and so on? And that's kind of a knowing what math is capable of. I also happen to think that math is one of the great kind of both intellectual and aesthetic creations of our civilization. And I think knowing something about sort of its history and what has been made possible in math is something that's very worthwhile. I mean, it's just like knowing cultural history, knowing other kinds of things like that, the history of what's been created in mathematics and some of the kind of elegant ideas that have been arisen in mathematics, even if you don't know in detail how to apply them. I think it's just something that is part of knowing about the culture and the development of our civilization. I am probably going to have to disappear in a few moments here because I have we have just started. We do a bunch of educational programs in the summer, and we have a summer school for kind of grown-ups. Occasionally we have high school students there, but usually it's kind of grown-ups, undergraduates, graduate students, postdocs, things like that. We have a science track, a technology track, an education track, and a physics track. And actually, just this next week, we're starting week 0 of our physics track. The main program is 3 weeks. The physics track has an extra week at the beginning. We also have a high school summer camp, which starts in about 2 weeks. That's a 2-week camp. And we also have a middle school camp. We just started this year, and I am supposed to go and do an event for that in a few minutes. And I'm kind of looking forward to that. That's a place where I actually get to do these kinds of Q&A discussions and so on, where I know who I'm talking to, and I can actually tell the middle school kids. Whereas here, I kind of have a suspicion that lots of you are sophisticated adults, which is great. But I like to keep these Q&As, if I can, accessible to kids. And so that's kind of affecting which questions I'm choosing to answer here and how I'm trying to answer them. But I think I will have to disappear for today. We've stored up a lot of really interesting questions here, which I will try and address at another time. Questions about yeah. So I think we should wrap up here for now, and I look forward to interacting with you all again on another episode of Science and Technology Q&A another week. So